Imagine taking a teaspoon of material so dense that it weighs as much as a full-grown elephant. Now imagine an entire star's worth of that material, crushed into a sphere no bigger than Earth. Inside this object, matter has entered a state so bizarre that the normal rules you learned in school simply do not apply. Atoms can no longer exist as you know them. Electrons are squeezed so tightly together that they push back not because of heat, not because of pressure in any ordinary sense, but because of a quantum mechanical rule that forbids them from being in the same state. This is what happens inside a white dwarf, and what holds it up against the crushing force of gravity is not fire, not fusion, not any familiar force. It is a law written into the deepest fabric of reality itself. And that law has a limit. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Every star you see in the night sky is fighting a war. It has been fighting that war since the moment it was born, and it will keep fighting until the day it dies. The war is simple. Gravity wants to crush the star into oblivion. It wants to pull every atom inward, compress everything into the smallest possible space. And the only thing stopping it, the only thing keeping that star inflated and glowing, is energy. Heat. The fury of nuclear fusion raging at its core, pushing outward against gravity's relentless inward squeeze. For billions of years, the two forces hold each other in check. Gravity pulls in, fusion pushes out. The star hangs in balance, suspended between collapse and explosion, in a state physicists call hydrostatic equilibrium. It is a tug of war on an almost unimaginable scale. Every second, the star converts millions of tons of matter into energy just to keep itself from caving in. Every second, gravity answers by pulling harder, and for most of a star's life, neither side wins. But here is what you need to understand. Fusion does not last forever. The fuel runs out, and when it does, when the furnace at the heart of a star finally goes dark, gravity is still there. Gravity does not get tired. Gravity does not run out of fuel. Gravity has been waiting, patiently, for billions of years, and when the fire stops, gravity wins. What happens next depends on how massive the star was. For the most massive stars, the ones 8 or 10 or 20 times heavier than the Sun, the collapse is catastrophic. The core implodes so violently that it triggers a supernova, one of the most powerful explosions in the universe. The outer layers of the star are blasted into space, while the core is crushed into something extraordinarily dense, a neutron star or even a black hole. But most stars are not that massive. Most stars, including our Sun, are modest by cosmic standards. They burn steadily for billions of years, and when they die, the end is not a violent explosion. It is something quieter, something stranger, something that creates an object so bizarre that the matter inside it stops following the rules you learned in school. That object is a white dwarf. And to understand what a white dwarf is, you first need to understand how an ordinary star like our Sun will die. The Sun is currently about 4.5 billion years old. It is roughly middle-aged. It has been burning hydrogen in its core since it formed from a collapsing cloud of gas and dust, and it has enough hydrogen left to keep doing so for another 5 billion years or so. Right now, the Sun is in what astronomers call the main sequence phase of its life. This is the long, stable period during which a star fuses hydrogen into helium in its core. The energy released by this fusion is what produces the light and heat that makes life on Earth possible. Every second, the Sun converts approximately 600 million tons of hydrogen into helium through a process called the proton-proton chain. In this process, 4 hydrogen nuclei, which are just individual protons, are fused together under extreme temperature and pressure to form a single helium nucleus. The helium nucleus has slightly less mass than the 4 original protons combined. That missing mass has been converted into energy according to Einstein's famous equation relating energy and mass. The amount of energy produced is staggering. The Sun radiates about 3.8 times 10 to the 26th watts of power in all directions, every second, continuously, and has been doing so for billions of years. This energy is what creates the outward pressure that balances gravity and keeps the Sun stable. But the hydrogen is not infinite. The Sun's core contains a finite amount of fuel, and as billions of years pass, that fuel is slowly consumed. The core gradually becomes richer in helium, the ash of hydrogen fusion, and poorer in hydrogen, the fuel. Eventually, After roughly 10 billion years of steady burning, the hydrogen in the core will be exhausted. Not the hydrogen in the entire star. There is still plenty of hydrogen in the outer layers. But the core, where temperatures and pressures are high enough for fusion to occur, will have converted all its hydrogen into helium. And this is where things begin to change dramatically. When the hydrogen runs out in the core, fusion stops there. The outward pressure that was holding the core up against gravity disappears. Gravity, which has been waiting patiently for billions of years, immediately begins compressing the core. The core contracts, and as it contracts, it heats up. This is a fundamental property of gravitational contraction. When you compress gas, it gets hotter. The core temperature rises, and this additional heat actually ignites hydrogen fusion in a thin shell surrounding the now inert helium core. This shell burning is unstable and produces more energy than the core fusion ever did. The extra energy causes the outer layers of the star to expand enormously. The star swells to many times its original size. Its surface cools as it stretches, turning from yellow-white to red. The star has become a red giant. When our Sun reaches this phase, roughly 5 billion years from now, it will expand so dramatically that it will engulf the orbits of Mercury and Venus. Earth may or may not be consumed, depending on exactly how large the Sun becomes, and whether Earth's orbit shifts outward as the Sun loses mass. But regardless, Earth's surface will be scorched beyond any possibility of life. The oceans will boil away. The atmosphere will be stripped off. The planet will be a barren, baked rock orbiting inside or near the outer atmosphere of a bloated, dying star. Meanwhile, the helium core continues to contract under gravity's relentless pressure. As it compresses, it grows hotter and denser. Eventually, if the star is massive enough, the core reaches a temperature of about 100 million degrees, roughly 7 times hotter than the core temperature during hydrogen burning. At this extreme temperature, helium nuclei begin fusing into carbon through a process called the triple alpha process. 3 helium nuclei, which are also called alpha particles, come together to form a single carbon nucleus. This requires 3 particles to collide almost simultaneously, which is extremely unlikely, which is why it requires such extreme temperatures and densities to occur at a meaningful rate. For a star like the Sun, helium ignition in the core happens in a dramatic event called the helium flash. The core has become so dense by this point that it is in a peculiar state, supported not by ordinary gas pressure, but by something called electron degeneracy pressure, a concept we will explore deeply later. In this state, the core does not expand and cool when fusion ignites, the way a normal gas would. Instead, the temperature spikes violently as fusion begins, producing an enormous burst of energy in a matter of seconds. The helium flash releases an incredible amount of energy, comparable to the luminosity of the entire Milky Way galaxy for a brief moment. But this energy is absorbed by the overlying layers and does not actually blow the star apart. Over time, the core heats up enough that normal gas pressure takes over again, the degeneracy is lifted, and the core expands to a new, stable equilibrium. Helium fusion then continues steadily for a time. But helium burning is much shorter lived than hydrogen burning. The Sun will burn helium in its core for only about 100 million years, compared to the 10 billion years it spent burning hydrogen. The helium is consumed more quickly because the temperatures are much higher, and because there is less fuel. When the helium in the core is exhausted, the core is left with carbon and some oxygen, the products of helium fusion. Now, for more massive stars, the story continues. The carbon core can contract further, heat up more, and ignite carbon fusion, producing neon, sodium, and magnesium. And the process can repeat, with each successive fuel burning at higher temperatures for shorter periods, building heavier and heavier elements, all the way up to iron. This is how the most massive stars build up layers of progressively heavier elements in their cores, like the layers of an onion. But for stars like the Sun, the story ends with carbon and oxygen. The Sun simply is not massive enough for its core to reach the temperatures required to fuse carbon. Carbon fusion requires temperatures of roughly 600 million to 1 billion degrees, and the Sun's core will never get that hot. The core contracts under gravity, but it never reaches the ignition point for carbon. It just gets denser and hotter without ever finding a new fuel to burn. So what happens? The star is dying. The core has no more fuel. Gravity is compressing it relentlessly. The outer layers, meanwhile, have become increasingly unstable. During the red giant and subsequent asymptotic giant branch phases, the star experiences powerful thermal pulses. These are periodic bursts of helium shell burning that send shockwaves through the star, causing it to pulsate. The outer layers are only loosely bound by gravity at this point. They have expanded so far from the core that the gravitational pull holding them is relatively weak. The thermal pulses, combined with strong stellar winds, gradually strip away the outer layers of the star. Over hundreds of thousands of years, the star sheds its outer atmosphere into space. This expelled material forms what is called a planetary nebula, one of the most beautiful objects in astronomy. The name is misleading. Planetary nebulae have nothing to do with planets. The term was coined in the 18th century by astronomer William Herschel, because through the small telescopes of that era, these objects looked like faint, round, greenish disks, somewhat resembling the planets Uranus and Neptune. The name stuck, even though we now know these are clouds of gas ejected by dying stars. Through modern telescopes, planetary nebulae display stunning shapes, rings, bubbles, hourglass figures, and intricate filamentary structures, all glowing in vivid colours as the expelled gas is ionized by the intense ultraviolet radiation from the exposed stellar core. And that exposed core is what we call a white dwarf. When the outer layers have been stripped away, what remains is the naked core of the former star. This core is composed primarily of carbon and oxygen, the ashes of helium burning. It is incredibly hot at its surface, often between 10,000 and 100,000 degrees or more, far hotter than the surface of the Sun today. It glows white or even blue-white with intense heat, which is where the name white dwarf comes from. But despite this extreme surface temperature, the white dwarf has no internal energy source. There is no fusion happening inside it, no nuclear reactions of any kind. The heat you see is residual. It is leftover thermal energy from the star's former life, slowly radiating away into space. The white dwarf is, in a sense, a cosmic ember, a glowing coal left behind after the fire has gone out. The size of a white dwarf is startling. Despite containing roughly the mass of the Sun, perhaps half a solar mass to about 1.4 solar masses, a white dwarf is only about the size of Earth. The Sun has a diameter of roughly 864,000 miles. Earth has a diameter of about 7,900 miles. A white dwarf takes the mass of something the size of the Sun and packs it into a volume comparable to our planet. That is an almost incomprehensible compression. If you could somehow take the Sun, remove its outer layers, and squeeze the remaining core down to the size of Earth, you would have a white dwarf. The implications for density are extraordinary, but we will explore that in detail shortly. For now, what matters is this. A white dwarf is the remnant core of a dead star. It has no fuel, it has no fusion, it has no internal energy source fighting gravity, and yet it does not collapse. It sits there, stable, holding itself up against gravity's pull for billions upon billions of years. This is the central mystery. In a normal star, fusion provides the energy that creates the pressure that holds the star up. Take away fusion, and you would expect the star to collapse. A ball of gas with no energy source should simply fall inward under its own weight. Gravity should crush it into something smaller and denser, and then smaller and denser still, until something stops it, or until it becomes a black hole. But a white dwarf does not collapse. It does not shrink any further. Something is holding it up. And that something is not heat. It is not the residual thermal energy left over from the star's active life. If you could somehow cool a white dwarf all the way down to absolute zero, removing every last bit of thermal energy, it would still not collapse. It would still maintain its size. It would still resist gravity's squeeze. This is one of the most remarkable facts in all of astrophysics. The pressure holding up a white dwarf has nothing to do with temperature. It is a completely different kind of pressure, one that arises not from the motion of hot particles, but from the quantum mechanical properties of electrons. This pressure is called electron degeneracy pressure, and it is unlike anything you encounter in everyday life. Understanding electron degeneracy pressure requires stepping away from the familiar world of gases, liquids, and solids, and entering the world of quantum mechanics. It requires understanding that electrons are not simply tiny balls bouncing around. They are quantum particles, governed by rules that have no analogy in our daily experience. And one of those rules, the Pauli exclusion principle, is what ultimately holds up a white dwarf against the force of gravity. But before we can understand degeneracy pressure, we need to understand just how extreme the conditions inside a white dwarf truly are. We need to grasp the density. Because the density of white dwarf matter is so far beyond anything in ordinary experience that it fundamentally changes how matter behaves. The rules that govern solids, liquids, gases, and even plasmas simply do not apply inside a white dwarf. The matter there exists in a state that has no name in everyday language, a state that can only be described using the language of quantum physics. Think about what it means to take the mass of the Sun and compress it into a volume the size of the Earth. The Sun is enormous, over 100 times wider than our planet, containing enough material to make more than 300,000 Earths. Now imagine squeezing all of that into a single Earth-sized sphere. The density you would get is so extreme that it dwarfs anything found anywhere on our planet. Not by a factor of 2 or 10 or even 100, by a factor of tens of thousands compared to the densest elements known to chemistry, and by a factor of millions compared to everyday materials like rock and water. These are densities so far beyond anything in our experience that every comparison we might reach for falls short. No material on Earth comes close. No laboratory can recreate these conditions. The only places in the universe where matter reaches this kind of compression are inside white dwarfs and in even more extreme objects like neutron stars. At these densities, the familiar structure of matter is destroyed. Atoms as you know them cease to exist. The electrons that normally orbit their nuclei in tidy quantum mechanical clouds are wrenched free. Not because the material is hot, the way a plasma strips electrons through violent thermal collisions, but because gravity has physically crushed the atoms beyond the point where their normal structure can survive. What remains is something entirely alien. A sea of liberated electrons flooding through a dense lattice of bare atomic nuclei, the whole mixture compressed into a volume that would be impossible to achieve through any force other than the weight of a star pressing in on itself from every direction. Understanding exactly how dense this material is, how it compares to anything you have ever encountered, and why this density forces matter into a state governed entirely by quantum mechanics, is where we need to go next. This state of matter is unlike any solid, liquid, or gas. In a gas, particles move freely and are widely separated. In a liquid, particles are close together but still mobile. In a solid, particles are locked into a crystal lattice. White dwarf matter is different from all of these. The nuclei may indeed form a crystalline lattice at low enough temperatures, but the electrons are not bound to any particular nucleus. They roam freely through the entire volume of the star, moving at tremendous speeds, occupying every available quantum state. This is sometimes described as a degenerate electron gas, but even that term is misleading because it suggests something gas-like, and this material behaves nothing like any gas you have ever encountered. The behavior of this electron sea is entirely dictated by quantum mechanics. Specifically, it is dictated by the fact that electrons are fermions, a class of particles that obey a rule called the Pauli exclusion principle. This principle, formulated by the Austrian physicist Wolfgang Pauli in 1925, states that no two identical fermions can occupy the same quantum state simultaneously. Two electrons cannot have the same position, the same momentum, and the same spin all at once. If one electron is in a particular quantum state, no other electron can be in that exact same state. They are forbidden from doubling up. This is not a suggestion. It is an absolute law of quantum mechanics, as fundamental and unbreakable as the speed of light. In ordinary matter, at everyday temperatures and densities, the Pauli exclusion principle does not make much of a difference in terms of bulk properties. There are so many available quantum states for the electrons to occupy, and the electrons have so much thermal energy allowing them to spread out among those states, that the exclusion principle is easily satisfied. Electrons simply avoid each other's states without any noticeable resistance. There is plenty of room for everyone, but in a white dwarf, the matter is compressed so tightly that the available quantum states become scarce. The electrons are packed into such a small volume that the lower energy states are all filled. Every low energy quantum state is occupied. If you try to compress the matter further, you are trying to force electrons into states that are already taken, and the Pauli exclusion principle absolutely forbids this. The electrons resist, they push back, not because they are hot, not because they are bouncing around energetically, but because the laws of quantum mechanics literally will not allow them to be squeezed any closer together. They have run out of quantum states to occupy, and the only way to accommodate more compression would be to force electrons into higher and higher energy states, which requires an ever-increasing amount of energy. This resistance to compression is electron degeneracy pressure. It is the force that holds up a white dwarf, and it is fundamentally different from any pressure you have encountered in ordinary life. Gas pressure depends on temperature. Heat a gas and it pushes harder. Cool it and the pressure drops. But degeneracy pressure does not depend on temperature at all. It depends only on density. Even at absolute zero, with no thermal energy whatsoever, degeneracy pressure would still exist. It is a purely quantum mechanical phenomenon, a direct consequence of the exclusion principle and the wave nature of matter. This is what makes a white dwarf so extraordinary. It is a star held up not by fire, not by heat, not by any ongoing energy source, but by a fundamental law of quantum mechanics. Gravity is trying to crush it. The exclusion principle is saying no, and as long as the white dwarf's mass does not exceed a certain critical threshold, the exclusion principle wins. The star remains stable, glowing quietly as it slowly radiates away its residual heat over billions upon billions of years. The first white dwarf ever discovered was the companion of Sirius, the brightest star in the night sky. In 1844, the German astronomer Friedrich Bessel noticed that Sirius was wobbling slightly in its motion across the sky. The wobble was subtle but unmistakable. Sirius was not travelling in a straight line through the galaxy. It was weaving back and forth, tracing a gently sinusoidal path against the background stars. Bessel deduced that it must have an unseen companion whose gravity was tugging on it, pulling it first one way and then the other as the two objects orbited their common centre of mass. In 1862, telescope maker Alvan Graham Clark actually observed this companion during a routine test of a new telescope lens, and it became known as Sirius B. It was extremely faint, far dimmer than expected for a star massive enough to make Sirius wobble so noticeably. When astronomers eventually measured its properties in the early 20th century, they were baffled. Sirius B had a mass roughly equal to the Sun, but a size comparable to Earth. The density implied by these measurements was so outrageous that many astronomers initially refused to believe it. The numbers simply did not make sense within the framework of classical physics. Arthur Eddington, one of the greatest astrophysicists of the early 20th century, famously described the situation by saying that the message of the companion of Sirius, when decoded, ran something like this: "I am composed of material 3,000 times denser than anything you have ever come across. A ton of my material would be a little nugget you could put in a matchbox." Eddington admitted he found this almost impossible to accept, but the observations left no alternative. The measurements had been checked and rechecked. The mass was real, the size was real, and the density, absurd as it seemed, was the inescapable consequence. It took quantum mechanics, a theory that was still being developed in the 1920s, to explain how such an object could exist. In 1926, Ralph Fowler applied the newly formulated Fermi-Dirac statistics, the mathematical framework describing the behaviour of fermions like electrons, to the problem of white dwarf structure. He showed that electron degeneracy pressure could support a star against gravitational collapse, even in the absence of any energy source. For the first time, physics had an explanation for these impossible objects. White dwarfs were not impossible at all. They were a natural consequence of quantum mechanics, operating under extreme gravitational compression. Today, we know that white dwarfs are among the most common stellar remnants in the universe. Roughly 97% of all stars in the Milky Way will end their lives as white dwarfs. Every star with a mass below roughly 8 solar masses, which includes the vast majority of all stars, will eventually shed its outer layers and leave behind a white dwarf core. The galaxy is filled with them. Astronomers have catalogued thousands, and there are likely billions more scattered throughout the Milky Way alone. They are everywhere, these quiet remnants, cooling slowly in the darkness, held up by nothing more than the stubbornness of electrons refusing to share their quantum states. And that is what makes the story of a white dwarf so compelling. It is not just a story about a dead star. It is a story about the fundamental nature of matter itself, about what happens when ordinary physics reaches its limits and quantum mechanics takes over, about the surprising ways the universe prevents its own collapse, not through force or energy, but through the deep mathematical rules governing the behaviour of subatomic particles. The fire is gone, the fuel is spent. Gravity should win, but it does not, because reality has rules that go deeper than fire and fuel, rules written into the fabric of quantum mechanics, rules that say electrons cannot be in the same state. And those rules, quiet and invisible, and operating at scales far too small for any human eye to see, are strong enough to hold up an entire star. To really understand what is happening inside a white dwarf, you need to confront the density. Not just acknowledge it as a large number, but sit with it, turn it over in your mind, and appreciate just how far beyond ordinary experience it truly is. Because the density of white dwarf matter is not just extreme. It is so extreme that it forces matter into a state that has no equivalent anywhere in your daily life. Not a solid, not a liquid, not a gas, not even a plasma. Something else entirely. Something that only exists under conditions so crushing that the very structure of atoms is destroyed. Let us start with what you know. The air you are breathing right now has a density of about 1.2 kilograms per cubic meter at sea level. That is incredibly thin. Air is mostly empty space, with molecules of nitrogen and oxygen bouncing around at high speeds, colliding with each other and with everything they touch. The molecules are far apart relative to their size. If you could see individual air molecules, they would be like gnats flying around in a cathedral. Vast distances between them compared to their own dimensions. This is what a gas is. Particles moving freely, widely separated, filling whatever container holds them. Water is much denser than air, about 1,000 kilograms per cubic meter, 1,000 times denser than the atmosphere. In water, molecules are packed closely together, touching their neighbours, sliding past each other. There is very little empty space between them. This is why water is nearly incompressible. You can squeeze air easily, because there is so much space between the molecules. But water resists compression, because the molecules are already as close together as they can get under normal conditions. Each water molecule is bumping up against its neighbours on all sides. Iron, one of the densest common materials, has a density of about 7,870 kilograms per cubic meter, nearly 8 times denser than water. In solid iron, atoms are locked into a crystal lattice, each atom held in place by metallic bonds, vibrating in position but not free to move around. The atoms are packed efficiently, filling space as tightly as their electron clouds allow. Gold is denser still, about 19,300 kilograms per cubic meter. Osmium, the densest naturally occurring element on Earth, reaches about 22,590 kilograms per cubic meter. These are the densest substances you will find anywhere on the surface of our planet. Now consider white dwarf matter. The average density of a typical white dwarf is roughly 1 million grams per cubic centimeter. Let me convert that so the comparison is direct. That is 1 billion kilograms per cubic meter. 1 billion. Compare that to osmium at roughly 22,590. White dwarf matter is approximately 44,000 times denser than the densest element found on Earth. It is roughly 1 million times denser than water. It is about 830 million times denser than air. These are not subtle differences. These are differences so vast that the materials might as well exist in different universes. The gap between air and water is a factor of about 1,000. The gap between water and white dwarf matter is a factor of 1,000,000. We have jumped so far beyond ordinary experience that every familiar reference point has been left behind. A sugar cube of white dwarf material, 1 cubic centimetre, would weigh about 1 metric ton on Earth. Imagine holding a sugar cube that weighs as much as a small car. Your hand could not support it. Your table could not support it. It would crash through the floor. It would crash straight through the foundation beneath the floor. It would sink into the ground like a bullet through wet paper. A teaspoon of this material, about 5 cubic centimetres, would weigh roughly 5 metric tons. That is heavier than a large elephant. 5 tons balanced on the tip of a teaspoon. A coffee mug filled with white dwarf material would weigh approximately as much as a fully loaded cargo ship. If you could gather enough white dwarf material to fill a bathtub, it would weigh roughly as much as an ocean liner. If you could fill a swimming pool, the mass would rival that of a small mountain. The numbers become absurd very quickly, which is precisely the point. We are not dealing with a material that is merely heavy. We are dealing with a material that is so fundamentally different from anything on Earth that our usual intuitions about weight, about solidity, about what matter is and how it behaves, simply break down completely. These comparisons are entertaining, but they also illustrate something important. The density of white dwarf matter is not just a bigger version of ordinary density. It represents a fundamental change in the nature of matter itself. At these densities, matter cannot exist in any form you would recognize. The forces and structures that give ordinary matter its properties have been overwhelmed and broken apart by gravitational compression. To understand why, you need to understand what ordinary matter actually looks like at the atomic level, and what happens to that structure when you try to compress it far beyond its natural limits. An atom, any atom, is mostly empty space. This is one of the most startling facts in physics, discovered through Rutherford's gold foil experiment in 1911. The nucleus of an atom, where almost all the mass resides, is incredibly tiny compared to the atom as a whole. A typical atomic nucleus has a diameter of roughly 1 to 10 femtometers. A femtometer is 1/400,000th of a meter. The atom itself, defined by the extent of its electron cloud, has a diameter of roughly 1 to 3 angstroms, where an angstrom is 1/10,000,000th of a meter. That means the atom is roughly 100,000 times wider than its nucleus. If you scaled the nucleus up to the size of a marble, about 1 centimeter across, the atom would be about 1 kilometer in diameter. A marble sitting in the middle of a sphere 1 kilometer wide. Everything between the marble and the outer edge of that sphere is effectively empty, occupied only by the ghostly probability clouds of electrons. In ordinary matter, this empty space is what gives materials their familiar densities. When atoms pack together in a solid, their electron clouds determine how closely they can approach each other. The electrons of one atom repel the electrons of neighbouring atoms through electromagnetic force. This repulsion sets a minimum distance between atomic nuclei in a solid. The atoms cannot get any closer because their electron clouds push back. This is why solids are hard. This is why you cannot push your hand through a table. The electron clouds of the atoms in your hand and the atoms in the table repel each other electromagnetically. The atoms themselves never actually touch in the classical sense. It is their electron clouds that interact, creating the sensation of solidity. In a gas, atoms or molecules are widely separated and move freely. If you compress a gas, you push the particles closer together. At low pressures, this is easy because there is plenty of space between them. As you compress further, the particles get closer and closer until eventually you reach a point where their electron clouds start to overlap. At this point, electromagnetic repulsion pushes back hard and the gas resists further compression. If you keep pushing, applying more pressure, you can force the material into a liquid state and then a solid state where atoms are packed as closely as their electron clouds allow. But what happens if you keep pushing beyond that? What happens if you apply pressures so extreme that even the electromagnetic repulsion between electron clouds is overwhelmed? This is exactly what gravity does inside a white dwarf. The gravitational pressure at the centre of a white dwarf is immense. The entire mass of half a sun or more is pressing inward from all directions, compressing the core material with a force that dwarfs anything achievable on Earth. Under this pressure, the normal structure of atoms is completely destroyed. The electron clouds that define the boundaries of individual atoms are crushed. Electrons are stripped from their nuclei. Not in the way that happens in a hot plasma, where thermal energy kicks electrons free. In a white dwarf, the electrons are squeezed free by sheer mechanical compression. The atoms are pressed together so tightly that there is no longer room for electrons to maintain their normal orbital configurations around individual nuclei. What you end up with is a sea of free electrons permeating a lattice of bare atomic nuclei. The carbon and oxygen nuclei that make up most of the white dwarf are packed far more closely together than atoms in any ordinary solid. In a normal carbon crystal like diamond, the spacing between carbon nuclei is about 1.5 angstroms, set by the size of the electron clouds. In a white dwarf, the nuclei are packed much more closely because the electron clouds that normally keep them apart have been destroyed. The nuclei still repel each other electrostatically because they are all positively charged, but the free electrons flowing between them provide a screening effect, partially neutralizing the repulsion and allowing the nuclei to exist at much closer separations than would be possible in ordinary matter. This is not a solid in any normal sense. It is not a liquid. It is not a gas. It is not even a conventional plasma, though it shares some features with one. In a plasma, atoms are ionized and electrons are free, but the particles are typically hot and energetic, moving at high speeds due to thermal energy. In a white dwarf, especially a cooled one, the thermal energy can be quite low. The electrons are not moving fast because they are hot. They are moving fast for an entirely different reason, one rooted in quantum mechanics. We will explore that reason in detail shortly, but for now, the important point is that white dwarf matter exists in a state that has no analogy in everyday experience. Physicists sometimes call it degenerate matter, but even that term does not convey the strangeness of what is happening. Let us think about density from another angle. In ordinary matter on Earth, the density is determined almost entirely by how closely atoms can pack together, which is determined by the size of their electron clouds. Atomic nuclei are incredibly dense, roughly 2.3 times 10 to the 17th kilograms per cubic meter, or about 230 trillion times the density of water. But atoms are mostly empty space, so the actual density of bulk matter is vastly lower than nuclear density. Ordinary solids reach maybe 20,000 kilograms per cubic meter at most, which is roughly 1 trillion times less dense than nuclear matter. The gap between ordinary density and nuclear density is enormous, spanning many orders of magnitude. White dwarf matter sits in this gap. It is far denser than any ordinary material, but far less dense than nuclear matter. It occupies an intermediate regime, where atoms have been destroyed but nuclei have not been crushed together. The electrons have been freed from their atoms and form a degenerate gas, while the nuclei float in this electron sea at separations much smaller than normal atomic spacings, but much larger than nuclear spacings. This intermediate density regime, roughly 10 to the 6th grams per cubic centimetre, is unique to white dwarfs. Nothing else in the universe occupies this particular density range in a stable configuration. Below this density, you get ordinary matter in its various familiar form. Above it, at densities approaching nuclear density, roughly 10 to the 14 grams per cubic centimetre, you get neutron star matter, which is even more extreme and operates on entirely different physics. To appreciate how different this is from anything on Earth, consider what would happen if you could somehow bring a chunk of white dwarf material to Earth's surface. First, it would be extraordinarily heavy. A piece the size of a basketball would weigh several 100,000 tons. It would immediately sink through any surface you placed it on, drilling through rock and metal like a hot knife through butter. The gravitational compression that holds white dwarf matter in its degenerate state would be absent on Earth's surface, where gravity is roughly 300,000 times weaker than at the surface of a white dwarf. Without that immense pressure, the degenerate matter would rapidly expand. The electrons, no longer confined by crushing gravity, would rearrange themselves around the nuclei, reforming ordinary atoms. The material would expand explosively as it reverted from degenerate matter to ordinary matter, releasing tremendous energy in the process. You could not actually hold a piece of white dwarf material in your hand, even in principle. It would either crush you with its weight or explode as it decompressed. This thought experiment illustrates something crucial. White dwarf matter is not just dense, ordinary matter. It is a fundamentally different state of matter that can only exist under the specific conditions found inside a white dwarf, namely extreme gravitational compression. Remove the compression and the matter ceases to be degenerate. It reverts to ordinary atoms. The degenerate state is maintained by the environment, by the crushing weight of the entire star pressing inward from all sides. The matter inside a white dwarf is trapped in this exotic state by gravity. Now here is the question that puzzled physicists in the early 20th century. If there is no fusion happening inside a white dwarf, what prevents it from collapsing further? Ordinary gas pressure depends on temperature. When a gas is hot, the particles move fast and push outward. When a gas cools, the particles slow down and the pressure drops. If a white dwarf had only ordinary gas pressure holding it up, then as it radiated away its heat and cooled over time, the pressure would decrease and gravity would compress it further. It would shrink as it cooled, and as it shrank, it would get denser. But if the pressure kept dropping with temperature, eventually nothing would stop the collapse. The white dwarf would implode under its own weight. But this does not happen. White dwarfs cool, but they do not shrink. They lose heat, but they do not collapse. Observations confirm this. White dwarfs that have been cooling for billions of years were the same size as younger, hotter white dwarfs of similar mass. The pressure holding them up was clearly not dependent on temperature. Something else was at work. Classical physics had no explanation for this. In the classical view of matter, all pressure comes from the thermal motion of particles. Faster particles mean more pressure. Slower particles mean less pressure. Zero temperature means zero pressure. A cold, dead stellar core with no energy source should have no outward pressure and should collapse under gravity. There is no way around this conclusion within classical physics. The answer, as we now know, comes from quantum mechanics. Specifically, it comes from the way electrons behave when they are packed together at extreme densities, and from a quantum mechanical rule called the Pauli exclusion principle that governs what configurations are allowed and what configurations are forbidden. But to understand how this works, we first need to appreciate just how strange a white dwarf is as a physical object, beyond even its density. Because the density alone does not capture the full weirdness. The physical behaviour of white dwarfs defies common sense in ways that point directly toward quantum mechanics as the only possible explanation. One of the most counterintuitive properties of a white dwarf is its relationship between mass and size. In everyday experience, heavier objects are bigger. A bowling ball is bigger than a marble. A planet with more mass has more volume. Jupiter is bigger than Earth because it contains more material. This seems obvious and universal. But white dwarfs violate this expectation completely. A heavier white dwarf is actually smaller than a lighter one. Adding mass to a white dwarf makes it shrink. This is the exact opposite of what happens with any ordinary object, and it is a direct consequence of the exotic pressure that supports these stars. The reason is that increasing the mass increases the gravitational compression. The interior is squeezed more tightly, packing the electrons into a smaller volume. The quantum mechanical pressure that holds the star up does increase in response, maintaining equilibrium, but the equilibrium point is at a smaller radius than before. More mass means more gravity, which means more compression, which means a smaller star. A white dwarf with half the mass of the Sun might be roughly 50% larger than Earth in radius. A white dwarf with the full mass of the Sun would be smaller, perhaps 80% of Earth's diameter. And a white dwarf approaching the maximum mass that can be supported is smaller still, squeezed down toward the breaking point of its quantum mechanical defense. If you could keep adding mass, the white dwarf would shrink further and further, growing denser and denser, until eventually the quantum pressure would be unable to keep up with gravity's increasing pull. But that breaking point is what makes the story truly dramatic. This bizarre inverse relationship was deeply confusing to astronomers when it was first discovered. It contradicted every intuition about how objects should behave. In the ordinary world, matter resists compression because of the electromagnetic repulsion between electron clouds. The more you squeeze, the harder it pushes back, and the object reaches a stable size that grows with the amount of material it contains. Bigger objects are made of more stuff and occupy more space. It is so intuitive that it hardly needs stating. But white dwarfs overturned this assumption entirely. They demonstrated that the pressure supporting them obeys fundamentally different rules from anything in the classical world. Rules where squeezing the star harder does make it push back harder, but not quite hard enough to prevent shrinking. Rules where equilibrium exists, but at a smaller size for a larger mass. This alone was powerful evidence that something beyond classical physics was governing white dwarf interiors. The surface conditions of a white dwarf are equally extreme. The surface gravity is roughly 100,000 to 1 million times stronger than Earth's surface gravity, depending on the mass and radius. If you weigh 70 kilograms on Earth, you would weigh somewhere between 7 million and 70 million kilograms on the surface of a white dwarf. Your body would be flattened into a film thinner than a sheet of paper in a fraction of a second. No human, no machine, no material we have ever built could withstand the gravitational forces at a white dwarf's surface. Even the atmosphere of a white dwarf is affected. The extreme gravity pulls the atmosphere down into an incredibly thin layer, perhaps only a few hundred meters thick, compared to Earth's atmosphere, which extends for hundreds of kilometers. Elements in this atmosphere stratify by weight with remarkable efficiency. Heavier elements sink below lighter ones in a matter of hours or days, because the gravitational pull sorting them is so ferocious that diffusion processes which would take geological ages on Earth are completed almost instantly on a white dwarf. This immense surface gravity has measurable effects on the light the white dwarf emits. According to Einstein's general theory of relativity, light climbing out of a gravitational field loses energy in the process. The photons are not slowed down. Light always travels at light speed. Instead, their wavelengths are stretched. They shift toward the red end of the spectrum. This is called gravitational redshift, and it was one of the earliest predictions of general relativity. In 1925, astronomer Walter Adams measured the spectrum of Sirius B and detected exactly this redshift. The light from Sirius B was shifted by an amount consistent with the enormous gravitational field predicted by its mass and size. This was powerful confirmation both that Sirius B was as dense as the measurements suggested, and that Einstein's theory of general relativity was correct. A single observation of a white dwarf helped confirm two revolutionary ideas simultaneously: the extreme density of stellar remnants and the curvature of spacetime by gravity. The gravitational redshift measurement was particularly important because it provided an independent check on the density. Before Adams made his observation, the density estimates for Sirius B were based on combining mass measurements from its orbital motion with size estimates from its luminosity and temperature. These were indirect measurements, and some astronomers questioned whether they could really be trusted. The gravitational redshift offered a completely different way to test the claim. General relativity predicted a specific redshift for a star of known mass and radius. When Adams measured the spectrum of Sirius B and found exactly the predicted shift, it closed the case. The density was real. Sirius B was as impossibly dense as the calculations said. White dwarfs also come in different varieties depending on the mass of the star that produced them. The most common type, and the type our Sun will eventually produce, is a carbon-oxygen white dwarf. These form from stars between roughly half a solar mass and about 8 solar masses. The core burns hydrogen into helium, and then helium into carbon and oxygen before the star sheds its outer layers. But lighter stars, those below about half a solar mass, may never reach the temperatures needed to ignite helium at all. Their cores are made of pure helium. These helium white dwarfs are smaller and less massive, and because no star below half a solar mass has had time to die in the current age of the universe, the helium white dwarfs we observe today were all produced through binary star interactions, where a companion star stripped away the outer layers prematurely. At the heavy end, stars between roughly 8 and about 10 solar masses may produce cores that burn carbon and oxygen into neon and magnesium before shedding their envelopes. These produce oxygen-neon white dwarfs, which are rarer and more massive. They sit closer to the maximum mass a white dwarf can support and are denser than typical carbon-oxygen white dwarfs. Each variety has slightly different properties, slightly different densities, slightly different cooling rates, but all share the same fundamental mystery. And the cooling itself reveals something remarkable about the physics at work. A white dwarf begins its life incredibly hot, with surface temperatures that can exceed 100,000 degrees. Over time, it radiates this heat into space and cools. You might expect this cooling to cause the star to shrink, the way a balloon deflates as the air inside it cools. In ordinary matter, cooling reduces thermal pressure, which allows gravity to compress the object further. But white dwarfs do not shrink as they cool. They maintain essentially the same size for billions of years, even as their temperatures drop by orders of magnitude. A young white dwarf at 50,000 degrees and an old white dwarf at 5,000 degrees, if they have the same mass, are virtually the same size. This is one of the most direct observational clues that the pressure holding them up has nothing to do with temperature. Whatever is supporting a white dwarf against gravity operates independently of how hot or cold the star is. It must be a pressure that depends on something else entirely, on some property that does not change as the star radiates away its thermal energy. Astronomers have observed thousands of white dwarfs at various stages of cooling, from blazing hot newborns fresh from their planetary nebulae to ancient embers that have been fading for billions of years. The cooling sequence is well studied and forms a reliable cosmic clock. Because white dwarfs cool at predictable rates, measuring the temperature of the oldest white dwarfs in a stellar population tells you the age of that population. The coolest white dwarfs in the Milky Way's disk have temperatures of about 3,500 to 4,000 degrees, which tells us the disk is roughly 8 to 9 billion years old. White dwarf cooling is one of the most precise age-dating tools in astrophysics, and it works precisely because the pressure holding them up does not depend on temperature, allowing the cooling to proceed in a clean, predictable way without the complication of structural changes. Regardless of composition, all white dwarfs share the same essential property. They are supported against gravitational collapse, not by heat, not by fusion, not by any ongoing energy source, but by the quantum mechanical behaviour of their electrons. Understanding exactly how this quantum support works, why it depends on density rather than temperature, why it involves rules that have no analogy in everyday experience, and ultimately, why it has a breaking point beyond which even quantum mechanics cannot prevent collapse, requires a deep journey into the quantum world. It requires understanding what electrons truly are, how they differ from the objects we see around us, and why a mathematical rule about the filling of quantum states can hold up an object with the mass of a star. That is where we are going next, and the story begins with a deceptively simple question. What happens when you try to put two electrons in exactly the same place, with exactly the same energy, moving in exactly the same way? Now we need to go deeper. We have established that white dwarf matter is extraordinarily dense, that atoms are crushed beyond recognition, and that the pressure holding the star up does not come from heat. But we have only sketched the outline of the real explanation. To truly understand what is happening inside a white dwarf, you need to understand the quantum mechanics behind it. Not just the names of the principles involved, but what they actually mean physically. Why do electrons resist being squeezed together? What is it about the quantum world that creates a pressure with no classical equivalent? And how can something as abstract as a mathematical rule about quantum states hold up an object the size of a planet against the gravitational pull of half a sun? The story begins with a deceptively simple observation about the nature of particles. In the everyday world, objects are distinguishable. You can tell one tennis ball from another. You can label them, track them, follow their individual paths. Even if two tennis balls are identical in size, weight, and colour, you can still distinguish them by their positions. This one is on the left, that one is on the right. You can follow each ball through time and always know which is which. Identical does not mean indistinguishable when you are dealing with macroscopic objects. But electrons are different. Two electrons are not just similar, they are absolutely, fundamentally identical. There is no property you can use to tell one electron from another. They have the same mass, the same charge, the same spin, the same everything. There are no hidden serial numbers, no tiny scratches on their surfaces, no subtle differences that a sufficiently powerful microscope could reveal. Every electron in the universe is exactly the same as every other electron. This is not an approximation or a simplification. It is a fundamental fact about the quantum world. Electrons are truly indistinguishable. This has profound consequences. In quantum mechanics, the state of a system of identical particles must respect this indistinguishability. If you swap two identical particles, the physical situation must be unchanged, because you cannot tell whether the swap happened or not. Mathematically, this means the wave function describing the system must either stay the same or change sign when you swap two particles. Particles whose wave functions stay the same under swapping are called bosons. Particles whose wave functions change sign are called fermions. This is not a minor technical distinction. It determines the fundamental behavior of matter. Photons, the particles of light, are bosons. They are perfectly happy to pile into the same quantum state. In fact, they prefer it. This is why lasers work. You can have billions of photons all in exactly the same quantum state, same energy, same direction, same polarization, all marching in lockstep. Bosons are gregarious, they like to be together. Electrons are fermions. They are the opposite. The anti-symmetry of the fermion wave function means that if two electrons are in the same quantum state, the wave function must be zero. A wave function of zero means zero probability of finding the particles in that configuration. It cannot happen. It is not just unlikely, it is impossible. This is the Pauli exclusion principle, and it is one of the most important laws in all of physics. Wolfgang Pauli formulated this principle in 1925 while trying to explain the structure of atoms. He was studying why electrons in atoms arrange themselves in specific patterns that had been observed spectroscopically but never explained from first principles. Why do atoms have the chemical properties they do? Why does the periodic table have its particular structure, with elements arranged in rows and columns that reflect repeating chemical behaviors? Why can the first shell of an atom hold only 2 electrons, the second shell 8, the third 18? The answer, Pauli realized, was that electrons in an atom cannot all crowd into the lowest energy state. Each quantum state can hold at most 1 electron, so the electrons fill up the available states from the bottom, each one occupying the next available slot. The first electron takes the lowest energy state with spin up. The second takes the same energy level but with spin down. That fills the first shell. The third electron must go to the next energy level, and so on, building up the electron configurations that give each element its unique identity. This filling pattern determines the electron configuration of atoms, which in turn determines their chemical behavior, which in turn determines the properties of every material in the universe. It is the reason carbon can form 4 bonds and create the complex molecules of life. It is the reason oxygen is reactive and helium is inert. It is the reason metals conduct electricity and wood does not. The exclusion principle is the reason chemistry exists. It is the reason you exist. Without it, all electrons would pile into the lowest energy state. Atoms would have no structure. There would be no chemical bonds, no molecules, no complexity, no life. Every material you have ever touched, every food you have ever eaten, every breath you have ever taken, owes its existence to this one quantum mechanical rule about fermions. In an ordinary atom sitting on your desk, the exclusion principle is at work, but its effects are subtle. There are relatively few electrons, typically between 1 and about 100, and plenty of available quantum states for them to occupy. The electrons settle into their assigned states without much fuss. The exclusion principle shapes the atom's structure, but it does not create any dramatic pressure or resistance to compression. There is room for everyone. But now imagine compressing matter to the densities found inside a white dwarf. You are taking roughly 10 to the 57th electrons, a number so large it is almost meaningless, and cramming them into a volume the size of Earth. The number of available quantum states in a given volume is finite. It depends on the volume and on the range of momenta the electrons can have. As you compress the material, the volume decreases. The number of low-energy states decreases with it, but the number of electrons stays the same. You have the same number of guests and fewer seats. The electrons fill the available states from the lowest energy upward. The lowest states fill first, then higher states, then higher still. As compression continues, more and more electrons are forced into higher and higher energy states because the lower ones are all occupied. The electrons at the top of the distribution, the ones in the highest occupied states, are moving very fast. Not because they are hot, not because anyone gave them kinetic energy, but because the exclusion principle left them no choice. Every slower state is already taken. The only states available to them are high-energy, high-momentum states. They are forced to move fast by the geometry of quantum state filling. This is where the Heisenberg uncertainty principle connects to the picture. Werner Heisenberg showed in 1927 that there is a fundamental limit to how precisely you can simultaneously know a particle's position and its momentum. The product of the uncertainty in position and the uncertainty in momentum must always be at least as large as a certain minimum value related to Planck's constant. This is not a statement about the quality of your measuring instruments. It is not a claim that we need better technology. It is a statement about the nature of reality itself. A particle simply does not have a precisely defined position and a precisely defined momentum at the same time. These properties are complementary. Knowing one with high precision necessarily means the other is spread out over a wide range of values. This is built into the wave nature of matter. Every particle is also a wave, and a wave that is localized to a small region must contain many different wavelengths, which correspond to many different momenta. You cannot have a wave that is both perfectly localized and perfectly monochromatic. It is mathematically impossible. If you confine a particle to a very small region of space, you know its position quite well. But the uncertainty principle then demands that its momentum be very uncertain, meaning it could have a wide range of momentum values, including very large ones. On average, confining a particle to a smaller space forces it to have a larger momentum and therefore move faster. This is not an abstract mathematical curiosity. It has measurable physical consequences. It is the reason atoms have a minimum size. If you tried to compress an electron's orbital to an infinitely small volume around the nucleus, the uncertainty principle would force its momentum to infinity, which would require infinite energy. The electron settles at a radius where the cost of confinement energy balances the benefit of being closer to the attracting nucleus. This is why hydrogen atoms have the size they do. The uncertainty principle sets the scale. In a white dwarf, the electrons are confined to a relatively small volume by the enormous gravitational pressure of the star. The uncertainty principle dictates that their momentum must be correspondingly large. Combined with the exclusion principle, which forces electrons into progressively higher momentum states as lower ones fill up, you get a population of electrons moving at tremendous speeds. Some of the electrons in a typical white dwarf are moving at roughly 1 to 2% of the speed of light. In the densest white dwarfs, electrons near the top of the Fermi distribution can reach 10% of the speed of light or more. These are extraordinary velocities, achieved not through heating, but through quantum mechanical confinement. These fast-moving electrons exert pressure. This is degeneracy pressure. Every electron careening through the interior of the white dwarf carries momentum. When it interacts with the surrounding material, when it is deflected or redirected, it transfers momentum. Momentum transfer per unit area per unit time is the definition of pressure. The faster the electrons move, the more momentum they carry, and the more pressure they exert. Since the electrons are moving fast, not because of temperature, but because of quantum state filling, this pressure exists independently of temperature. Cool the white dwarf to absolute zero, and the electrons are still moving fast, still carrying momentum, still exerting pressure. The degeneracy pressure remains. Let me try to make this more intuitive with a physical picture. Imagine a concert hall with numbered seats. Each seat can hold exactly one person. People enter and fill the seats starting from the front row. When the front row is full, they fill the second row, then the third. As the hall fills up, people are forced to take seats farther and farther from the stage. Now imagine the hall is completely packed. Every seat is taken. If you try to push more people into the hall, they cannot find seats. There is no room. The crowd pushes back against you, not because the people are agitated or energetic, but simply because there is no space left. This is a rough analogy for degeneracy pressure. The electrons are not pushing back because they are hot. They are pushing back because the quantum states are full. There is no room for them to be compressed any further, because every available state is already occupied. Now contrast this with a classical gas, an ordinary gas made of particles that do not obey the exclusion principle. In a classical gas, the particles bounce around with speeds determined by the temperature. Hot gas means fast particles and high pressure. Cold gas means slow particles and low pressure. If you cool the gas to absolute zero, the particles stop moving and the pressure drops to zero. The concert hall empties. Everyone leaves. There is no resistance to compression at zero temperature. But in a degenerate gas, the concert hall is still full even at absolute zero. You cannot empty it. The exclusion principle keeps every seat occupied. The particles do slow down as the gas cools, but they cannot all stop. If they all stopped, they would all be in the same quantum state, zero momentum, zero energy, and the exclusion principle forbids that. Only one electron can have zero momentum with spin up, and one with spin down. All the others must have non-zero momentum. At absolute zero, the degenerate gas is in its ground state, the lowest possible energy configuration. But that ground state still has enormous kinetic energy, because all the states up to the Fermi energy are filled with electrons moving at various speeds. The Fermi energy itself can be very large if the density is high. In a white dwarf, the Fermi energy corresponds to electron speeds that are a significant fraction of the speed of light. The Fermi energy is a crucial concept. It is the energy of the highest occupied quantum state at absolute zero. Below the Fermi energy, every state is filled. Above it, every state is empty. The Fermi energy depends on the density of the fermions. Pack more electrons into a smaller volume, and the Fermi energy goes up because more states need to be filled to accommodate all the electrons. Higher Fermi energy means faster electrons at the top of the distribution. Faster electrons mean more pressure. This relationship between density and Fermi energy is what makes degeneracy pressure increase with compression. If gravity squeezes the white dwarf a little, increasing the density, the Fermi energy rises. The electrons at the top of the distribution move even faster. The degeneracy pressure increases. This increase in pressure resists the additional compression, pushing back against gravity and restoring equilibrium. It is a stable arrangement. If you try to compress it further, the pressure goes up and pushes back harder. If you let it expand, the pressure drops and gravity pulls it back in. The white dwarf sits at the equilibrium point where degeneracy pressure exactly balances gravitational pull. This is a fundamentally different kind of stellar equilibrium than what exists in a normal star. In a main sequence star like the Sun, the equilibrium is maintained by a thermostat. If the core gets a little hotter, fusion rates increase, producing more energy, which increases pressure, which expands the core. The expansion cools the core, which reduces fusion rates, which reduces pressure, and the core contracts back to equilibrium. The star regulates itself through the temperature dependence of nuclear fusion rates. It is a dynamic, feedback-driven equilibrium. In a white dwarf, there is no thermostat. There is no fusion. There is no feedback loop involving temperature. The equilibrium is purely mechanical. Gravity pushes in. Degeneracy pressure pushes out. They balance. Temperature is irrelevant to this balance. The white dwarf could be at 1,000,000 degrees or absolute zero. The equilibrium would be the same because the pressure does not care about the temperature. It cares only about how many electrons are packed into how much space. Now, it is important to distinguish white dwarf matter from the matter found in even more extreme objects like neutron stars. In a white dwarf, electron degeneracy pressure does the work. The electrons are the degenerate particles, the ones filling quantum states and generating pressure. The nuclei, the carbon and oxygen nuclei that make up most of the mass, are not degenerate. They are too heavy. At white dwarf densities, the nuclei are spaced far enough apart relative to their quantum wavelengths that quantum effects on the nuclei are minimal. The nuclei behave more or less classically. They may form a crystal lattice, especially as the white dwarf cools, but they do not contribute significant degeneracy pressure. Their role is to provide mass, and therefore gravitational compression. The electrons do all the heavy lifting when it comes to supporting the star. In a neutron star, the situation is entirely different. Neutron stars are far denser than white dwarfs, roughly 100 million times denser. At these extraordinary densities, roughly 10 to the 14 grams per cubic centimeter, comparable to the density of an atomic nucleus itself, even electron degeneracy pressure is overwhelmed. The electrons can no longer support the star. Gravity has pushed past the point where electron quantum states can provide enough resistance. The electrons and protons in the material are forced together by gravitational compression and undergo a process called inverse beta decay, in which an electron and a proton combine to form a neutron and a neutrino. The electron essentially merges with the proton. It ceases to exist as a separate particle. The neutrino escapes, carrying away energy and leaving behind a neutron. Throughout the collapsing core, trillions upon trillions of these reactions occur nearly simultaneously, converting what was once a mixture of electrons, protons, and neutrons into almost pure neutron matter. And now it is the neutrons, which are also fermions, and therefore also obey the Pauli exclusion principle, that provide the degeneracy pressure. Neutron degeneracy pressure is much stronger than electron degeneracy pressure at any given density, because neutrons are nearly 2,000 times heavier than electrons. Their greater mass means that at a given density, their momenta and kinetic energies are different, and crucially, the densities required to make neutron degeneracy significant are vastly higher. So there is a clear hierarchy of exotic matter states. At ordinary densities, matter is made of intact atoms held together by electromagnetic forces. At white dwarf densities, around 10 to the 6 grams per cubic centimetre, atoms are destroyed, electrons form a degenerate gas, and electron degeneracy pressure supports the star. At neutron star densities, around 10 to the 14 grams per cubic centimetre, even the electrons and protons are crushed together into neutrons, and neutron degeneracy pressure takes over. Each stage represents a deeper level of gravitational compression, a more extreme destruction of ordinary matter, and the activation of a new quantum mechanical mechanism to resist further collapse. Between these regimes is a gap so enormous that white dwarf matter and neutron star matter are fundamentally different substances. A white dwarf is made of carbon and oxygen nuclei, bathed in a degenerate electron sea. A neutron star is made almost entirely of neutrons, packed together at nuclear densities. They are as fundamentally different from each other as water is from iron, as air is from diamond. Comparing them is like comparing two entirely different states of matter, operating on entirely different physical principles at entirely different scales of compression. The fact that both involve degeneracy pressure is almost coincidental. The underlying physics is very different. It is also worth noting what white dwarf matter is not. It is not a crystal in any ordinary sense, although the nuclei inside an old, cool white dwarf may indeed arrange themselves into a crystalline lattice. When this happens, the white dwarf is sometimes described as a giant crystal in space, which is a beautiful image and not entirely wrong. But the lattice of nuclei is only part of the story. The electrons permeating the lattice are degenerate and behave nothing like the electrons in a normal crystal. In a normal crystal like diamond or quartz, electrons are either locked into chemical bonds between specific atoms or occupy energy bands determined by the crystal's structure. In a white dwarf crystal, the electrons are free, not bound to any particular nucleus, and their behaviour is governed entirely by degeneracy rather than by the crystal structure. The lattice provides a scaffold for the nuclei, but the pressure, the thing that actually holds the star up, comes from the electrons flowing through and around that scaffold. It is a crystal unlike any crystal found on Earth, permeated by a quantum fluid of degenerate electrons that no terrestrial material remotely resembles. White dwarf matter is also not a plasma in the conventional sense. A plasma is an ionized gas in which electrons have been stripped from atoms by thermal energy. The sun's interior is a plasma. The gas inside a neon sign is a plasma. Lightning creates a plasma channel through the air. In all these cases, the ionization is driven by high temperatures. The particles are hot and energetic. Collisions between particles are violent enough to knock electrons loose from atoms. White dwarf matter is ionized, yes. The electrons are free from their nuclei, yes. But the ionization was not caused by heat. It was caused by compression, and the behavior of the electrons is not governed by thermal physics. It is governed by quantum statistics. Calling white dwarf matter a plasma would be technically incomplete and deeply misleading, because it would suggest that the material behaves like a hot, ionized gas, which it emphatically does not. So what is white dwarf matter? It is something that exists only in the language of quantum mechanics. It is a degenerate Fermi gas of electrons, coexisting with a lattice or fluid of bare atomic nuclei, held in its extreme configuration by the gravitational compression of a stellar mass object. Every word in that description matters. Degenerate means the quantum states are filled from the bottom up. Fermi gas means the particles are fermions obeying the exclusion principle. Electrons specifies which fermions are providing the pressure. Bare atomic nuclei specifies what provides the mass and the gravitational compression, and stellar mass tells you the scale required to create the conditions where this state of matter can exist. There is a profound lesson here about the relationship between quantum mechanics and the macroscopic world. We often think of quantum mechanics as the physics of the very small, relevant only to atoms and subatomic particles, with no visible effects at human scales. This is broadly true in everyday life. You do not need quantum mechanics to drive a car or cook dinner. But white dwarfs demonstrate that quantum mechanics can have consequences at the largest scales imaginable. The Pauli exclusion principle, a rule governing the behavior of individual electrons, is what holds up an object with the mass of a star. A quantum mechanical principle operating at scales of 10 to the negative 15 meters is determining the structure of an object 10 million meters across. The ratio between these scales is roughly 10 to the 22. That is like a rule governing something smaller than a single atom, determining the behavior of something larger than a planet. Quantum mechanics reaches up from the subatomic world and grabs hold of the cosmos itself. This is not an isolated or unusual example. Quantum mechanics shapes the macroscopic universe in many surprising and profound ways. The stability of ordinary matter depends on the exclusion principle. Without it, atoms would collapse, and matter would not have the properties that allow chemistry, biology, and life. The colors of stars depend on quantum mechanical energy levels in atoms. The nuclear fusion that powers stars depends on quantum tunneling, the ability of particles to pass through energy barriers that classical physics says they should not be able to cross. Radioactive decay, which heats the interiors of rocky planets and drives plate tectonics on Earth, is a quantum mechanical process. The behavior of semiconductors, which makes modern electronics possible, depends entirely on quantum mechanics. But the white dwarf represents perhaps the most dramatic example. An entire star held up against gravitational collapse by a rule about electrons. Subramanian Chandrasekhar, the Indian-American astrophysicist who would later win the Nobel Prize in Physics, was among the first to work out the detailed physics of electron degeneracy in white dwarfs. In 1930, at the age of just 19, while travelling by ship from India to England to begin his graduate studies at Cambridge, Chandrasekhar calculated the structure of white dwarfs using the newly developed framework of quantum mechanics, combined with Einstein's special theory of relativity. What he discovered during that voyage would reshape our understanding of stellar physics and lead to one of the most important results in astrophysics. But the implications of his calculation, particularly what happens when degeneracy pressure reaches its limit, are so significant that they deserve their own careful treatment. Because here is the thing about electron degeneracy pressure that makes the story of white dwarfs not just strange, but dramatic. Degeneracy pressure is powerful, but it is not infinite. There is a maximum mass that a white dwarf can support. Beyond that mass, even quantum mechanics cannot save the star from collapse. And what happens when that limit is exceeded is one of the most violent and consequential events in the universe. The pressure that holds up a white dwarf depends on how fast the electrons are moving. As the white dwarf's mass increases, gravity's inward pull strengthens, and the star must compress further to generate enough degeneracy pressure to balance gravity. Greater compression means higher density. Higher density means the electrons are forced into higher energy states. Higher energy states mean faster electrons, and as long as the electrons can keep moving faster, the pressure can keep rising to match gravity's increasing pull. But there is a speed limit built into the fabric of the universe. Nothing can move faster than the speed of light. As the white dwarf's mass increases and the electrons are forced to move faster and faster, they begin to approach this ultimate speed limit. And as they approach the speed of light, something changes in the relationship between compression and pressure. The pressure no longer rises as quickly with increasing density. The electrons are approaching the fastest they can possibly move. They are running out of room to accelerate. The pressure is approaching its maximum, and gravity has not yet reached its maximum because you can always add more mass. This is the seed of the crisis that defines the ultimate fate of white dwarfs. Quantum mechanics holds the star up, but only up to a point. Beyond that point, even the deepest rules of quantum physics are not enough to prevent catastrophe. And that critical threshold, that precise breaking point, has a name. It is called the Chandrasekhar limit. So electron degeneracy pressure holds up a white dwarf. Quantum mechanics provides a force that resists gravitational collapse without needing any fuel, any heat, any ongoing energy source. It sounds like an unbeatable defense. Gravity pushes in, and the exclusion principle pushes back, indefinitely, without ever getting tired, without ever running out. You might think that this means a white dwarf can support any amount of mass, that no matter how heavy the stellar remnant, the electrons will always find higher energy states to occupy, will always move a little faster, will always generate enough pressure to hold the star up. But that is not what happens. Because there is a cosmic speed limit, and the electrons eventually run into it. Nothing in the universe can travel faster than the speed of light. This is not a practical limitation. It is not something we might overcome with better engineering or more advanced technology. It is a fundamental law of physics, woven into the structure of space-time itself by Einstein's theory of special relativity. The speed of light in a vacuum is approximately 299,792 kilometers per second. It is absolute, it is unchangeable, and it applies to everything, including electrons inside a white dwarf. As a white dwarf's mass increases, gravity pulls harder. To maintain equilibrium, the degeneracy pressure must increase to match. Higher pressure requires the electrons to occupy higher energy states, which means moving faster. In a low-mass white dwarf, the electrons at the top of the Fermi distribution might be moving at a few percent of the speed of light. This is already extraordinarily fast by everyday standards, but it is well below the relativistic regime, where Einstein's corrections become important. At these speeds, the classical equations describing degeneracy pressure work well. The relationship between density and pressure is straightforward. Compress the star a little, and the pressure rises proportionally. The star adjusts smoothly and finds a new, slightly smaller equilibrium. But as the mass increases and the star compresses further, the fastest electrons begin to approach a significant fraction of the speed of light. At 10% of light speed, relativistic effects are noticeable but small. At 50%, they are substantial. At 90%, the physics changes dramatically. And this is where the trouble begins. In classical Newtonian mechanics, there is no speed limit. If you push harder on an object, it accelerates more. Apply twice the force, get twice the acceleration. The relationship between force and acceleration is simple and linear. You can always make something go faster by pushing harder, but special relativity changes this. As an object approaches the speed of light, it becomes harder and harder to accelerate. Its effective inertia increases. The same force that once produced a noticeable acceleration now produces barely any change in speed. As velocity approaches the speed of light, the energy required to accelerate further approaches infinity. You can never actually reach the speed of light because doing so would require infinite energy. This has a devastating consequence for electron degeneracy pressure. In the non-relativistic regime, when electrons are moving well below light speed, compressing the star forces electrons into higher momentum states, and they respond by moving significantly faster. Their kinetic energy rises sharply. The pressure increases robustly with increasing density. There is plenty of headroom. Push harder, and the electrons push back proportionally harder. The system is stable and responsive. But in the relativistic regime, when electrons are already moving close to the speed of light, compressing the star further still forces electrons into higher momentum states. Their momenta increase, yes, but their velocities barely change, because they are already near the speed limit. An electron moving at 95% of the speed of light, and one moving at 98% of the speed of light, have very different momenta, but almost the same velocity. The additional momentum translates into increased relativistic mass, rather than increased speed. And because their velocities are barely increasing, the pressure does not rise as steeply with density as it did before. The pressure is still growing, but it is growing more slowly, and gravity is not slowing down at all. This is the crux of the problem. In the non-relativistic case, degeneracy pressure increases with density raised to the 5/3 power. This is a steep relationship. Double the density, and the pressure increases by about 3.2 times. The pressure rises quickly enough to counteract any increase in gravitational compression. But in the ultra-relativistic case, when the electrons are moving at nearly the speed of light, the relationship changes. Degeneracy pressure now increases with density raised to only the 4/3 power. Double the density, and the pressure increases by about 2.5 times. This is a shallower relationship. The pressure still increases with density, but not as fast. Why does this matter? Because gravity also becomes stronger as the star shrinks. When a star contracts, the mass is packed into a smaller volume, and the gravitational pressure at the center increases. The rate at which gravity strengthens with increasing density depends on the mass of the star. For a sufficiently massive white dwarf, gravity strengthens with density faster than relativistic degeneracy pressure does. At some critical mass, gravity wins. No matter how much further you compress the star, no matter how high the density goes, the degeneracy pressure can never catch up. Gravity always pulls harder than quantum mechanics can push back. The star is doomed to collapse. This critical mass is called the Chandrasekhar limit, named after the physicist who first calculated it. Subramanian Chandrasekhar was born in Lahore in 1910, in what was then British India. He showed extraordinary mathematical talent from a young age. His uncle, Sir Chandrasekhar Venkataraman had won the Nobel Prize in Physics in 1930 for his discovery of light scattering effects. Physics ran in the family. Chandrasekhar studied at the University of Madras, where he excelled in mathematics and theoretical physics, devouring the latest papers on quantum mechanics and relativity that were revolutionizing European physics. In 1930, at the age of 19, Chandrasekhar boarded a steamship from India to England, where he had won a scholarship to study at the University of Cambridge under the supervision of Ralph Fowler, the very physicist who had first applied quantum mechanics to white dwarfs. The voyage took several weeks. And during those weeks, with nothing but time and his mathematical abilities, Chandrasekhar set about extending Fowler's work. Fowler had shown that electron degeneracy pressure could support a white dwarf, but Fowler had used non-relativistic quantum mechanics. He had not accounted for what happens when the electrons move close to the speed of light. Chandrasekhar realized this was a crucial omission. He incorporated Einstein's special relativity into the equations of white dwarf structure and worked through the mathematics on the ship. What he found was startling. When he included relativistic effects, the equations no longer guaranteed a stable solution for every mass. Below a certain critical mass, the equations gave well-behaved solutions. The white dwarf had a definite size and density, with degeneracy pressure balancing gravity. But above that critical mass, no stable solution existed. The equations said the star could not hold itself up. Degeneracy pressure, even at its maximum, was insufficient to counteract gravity. The critical mass Chandrasekhar calculated was approximately 1.4 solar masses. This is the Chandrasekhar limit. Any white dwarf with a mass below about 1.4 times the mass of the Sun can be supported by electron degeneracy pressure. Any stellar remnant above this mass cannot be a stable white dwarf. Something else must happen. The exact value of the Chandrasekhar limit depends slightly on the composition of the white dwarf. For a white dwarf made of pure carbon, the limit is about 1.44 solar masses. For one made of pure iron, it would be slightly different. For the typical carbon-oxygen composition found in most white dwarfs, the standard value quoted is approximately 1.4 solar masses. This number emerges directly from the fundamental constants of nature. It depends on Planck's constant, which governs quantum mechanics. It depends on the speed of light, which sets the relativistic speed limit. It depends on the gravitational constant, which determines how strong gravity is. And it depends on the mass of the proton, which determines how many electrons are available per unit mass. These are some of the most fundamental numbers in physics. The Chandrasekhar limit is not an accident or an approximation. It is a precise consequence of the deepest laws of nature. When Chandrasekhar arrived in Cambridge and presented his results, the reaction was not what he expected. Arthur Eddington, who was at that time one of the most famous and influential astrophysicists in the world, publicly rejected Chandrasekhar's conclusion. Eddington found the idea that a star above a certain mass could not find a stable endpoint deeply troubling. If a star above 1.4 solar masses could not become a white dwarf, what would happen to it? It would have to keep collapsing. But to what? Eddington found this prospect absurd. He believed nature must have a way to prevent indefinite collapse. At a meeting of the Royal Astronomical Society in 1935, Eddington dismissed Chandrasekhar's work, calling the mathematical result a reductio ad absurdum. He argued that there must be some unknown physical process that would prevent the collapse, that the laws of physics would not allow such a thing. Chandrasekhar was humiliated. Here was a young, unknown physicist from India being publicly contradicted by the most celebrated astrophysicist in Britain. The experience was painful, and Chandrasekhar later moved to the United States, where he spent the rest of his career at the University of Chicago. But Chandrasekhar was right. The mathematics was correct. The physics was sound. And eventually, the astrophysics community came to accept the Chandrasekhar limit as one of the foundational results in stellar physics. In 1983, Chandrasekhar was awarded the Nobel Prize in Physics for his theoretical studies of the physical processes important to the structure and evolution of stars, including his work on the mass limit of white dwarfs. The recognition came more than 50 years after his original calculation on that steamship from India to England. So what happens when a stellar remnant exceeds the Chandrasekhar limit? There are several scenarios, and each one leads to some of the most dramatic events in the universe. The first scenario involves a solitary massive star, one significantly heavier than the Sun. When such a star dies, the core left behind after nuclear burning ceases may be more massive than 1.4 solar masses. If the core mass is between roughly 1.4 and about 3 solar masses, the collapse does not stop at the white dwarf stage. Electron degeneracy pressure is insufficient. the core keeps collapsing. Electrons and protons are forced together, producing neutrons and neutrinos through inverse beta decay. The core collapses until it reaches nuclear density, roughly 10 to the 14 grams per cubic centimeter, where neutron degeneracy pressure halts the collapse. The result is a neutron star, an object only about 12 miles across, but containing more mass than the Sun. The collapse of the core triggers a supernova explosion, one of the most energetic events in the cosmos, blasting the outer layers of the star into space at speeds of tens of thousands of kilometers per second. The supernova can briefly outshine an entire galaxy, releasing more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. If the core mass exceeds roughly 3 solar masses, even neutron degeneracy pressure cannot hold it up. This upper limit for neutron stars is called the Tolman-Oppenheimer-Volkoff limit. Above this mass, nothing known in physics can prevent the collapse. The core collapses past nuclear density, past any known state of matter, and forms a black hole. A region of spacetime so severely curved that nothing, not even light, can escape. The matter is crushed into a singularity, a point of theoretically infinite density, where our current understanding of physics breaks down completely. General relativity predicts the singularity but cannot describe it. Quantum gravity, the yet undiscovered theory that unifies quantum mechanics and general relativity, is needed to explain what actually happens at the center of a black hole. The second scenario is perhaps even more spectacular. It involves a white dwarf in a binary system, orbiting closely with a companion star. If the companion is a normal star, a main sequence star, or a red giant, and the two are close enough, the white dwarf's intense gravity can pull matter from the companion's outer layers. This matter streams across the gap between the two stars, forming a swirling disk of gas called an accretion disk around the white dwarf. The gas spirals inward, heating up through friction, and eventually falls onto the white dwarf's surface. Each bit of accreted matter adds to the white dwarf's total mass. Slowly, over millions of years, the white dwarf gains mass from its companion. As the white dwarf's mass approaches the Chandrasekhar limit, the interior grows denser and hotter. The carbon and oxygen nuclei in the core, which have sat inert for billions of years, begin to reach temperatures where carbon fusion can ignite. But unlike in a normal star, where rising temperature causes expansion and cooling in a self-regulating feedback loop, the degenerate matter in a white dwarf does not expand when it heats up. Degeneracy pressure does not depend on temperature, so the temperature rises but the density stays the same. The fusion rate increases with temperature, producing more heat, which raises the temperature further, which increases the fusion rate even more. There is no thermostat, there is no regulation. It is a runaway thermonuclear explosion. In a matter of seconds, the entire white dwarf detonates. Not just the core, the entire star. Carbon and oxygen fuse explosively into heavier elements, silicon, sulfur, calcium, nickel, and iron, releasing an almost incomprehensible amount of energy. The white dwarf is completely destroyed. Nothing remains. No remnant, no neutron star, no black hole. Just an expanding cloud of debris flying outward at tens of thousands of kilometers per second, glowing with the brilliance of billions of suns. This is a Type 1a supernova, and it is one of the most important phenomena in all of astrophysics. The explosion synthesizes roughly half a solar mass of radioactive nickel-56, which decays first into cobalt-56 and then into stable iron-56 over the following weeks and months. It is this radioactive decay that powers the supernova's visible light, causing it to brighten over about 3 weeks and then slowly fade over the following months in a characteristic light curve that astronomers can recognize across billions of light years. Because every Type 1a supernova involves essentially the same event, a white dwarf detonating near the Chandrasekhar limit, they all produce roughly the same peak brightness. This remarkable uniformity makes them standard candles, objects of known luminosity that astronomers can use to measure distances across the universe. By comparing how bright a Type 1a supernova appears to how bright it actually is, astronomers can calculate how far away it is. This technique has been used to measure distances to galaxies billions of light years away, and it was precisely this technique, using Type 1a supernovae as distance markers, that led to one of the most stunning discoveries in the history of science. In 1998, 2 independent teams of astronomers studying distant Type 1a supernovae discovered that the expansion of the universe is accelerating. The galaxies are not just moving apart, they are moving apart faster and faster over time, driven by a mysterious force called dark energy that permeates all of space. This discovery, which earned the 2011 Nobel Prize in Physics, was made possible by the Chandrasekhar limit. The fixed mass at which white dwarfs explode is what gives Type 1a supernovae their uniform brightness. And that uniform brightness is what allowed astronomers to map the expansion history of the cosmos. A quantum mechanical limit on the mass of a dead star turned out to be the key to discovering the fate of the entire universe. Now let us consider the long-term future of white dwarfs that do not explode. The ones that sit safely below the Chandrasekhar limit, alone in space, or in wide binary systems where no mass transfer occurs. What happens to them over the eons? They cool. That is the simple answer. A white dwarf has no energy source, no fusion, no gravitational contraction, because degeneracy pressure prevents further shrinking. All it can do is radiate away the thermal energy stored in its interior, the residual heat left over from its former life as a star. And this cooling takes an extraordinarily long time. A young white dwarf might have a surface temperature of 50,000 or even 100,000 degrees, glowing brilliant blue-white. Over hundreds of millions of years, it cools to 10,000 degrees, shining white. Over billions of years, it cools further, passing through yellow, orange, and eventually red, its luminosity dropping steadily as the thermal reservoir depletes. The cooling rate itself changes as the white dwarf ages. Hotter white dwarfs radiate more intensely and cool faster. Cooler white dwarfs radiate less and cool more slowly. The process decelerates over time, stretching out longer and longer as the star grows dimmer and dimmer. As the temperature drops, something remarkable happens inside. The carbon and oxygen nuclei, which have been in a fluid-like state at high temperatures, begin to crystallize. The ions settle into a regular lattice structure, arranging themselves into a crystal that grows from the center outward. The white dwarf is literally freezing solid, forming a giant crystal sphere in space. This crystallization releases latent heat, the same kind of energy released when water freezes into ice, which temporarily slows the cooling process. The white dwarf enters a phase where it dims more slowly than expected, because the crystallization energy provides an additional source of heat. Astronomers have detected evidence of this crystallization in real white dwarfs. In 2019, a study using data from the European Space Agency's Gaia spacecraft identified a population of white dwarfs that appeared to pile up at certain luminosities and temperatures, exactly where crystallization theory predicted they should slow down in their cooling. This was direct observational evidence that white dwarfs undergo a phase transition from liquid to solid, forming crystals in their interiors. The cores of these ancient stellar remnants are literally turning into cosmic diamonds, enormous spheres of crystallized carbon and oxygen drifting through the galaxy. After crystallization is complete and the latent heat has been radiated away, the white dwarf continues to cool. Its surface temperature drops into the thousands of degrees, then the hundreds, then lower still. Its glow shifts from visible light into the infrared, becoming invisible to the naked eye but still detectable with infrared telescopes. Eventually, over timescales far longer than the current age of the universe, the white dwarf will cool to the temperature of the cosmic microwave background radiation, about 2.7 Kelvin, just a few degrees above absolute zero. At that point, it will be in thermal equilibrium with its surroundings, absorbing as much energy from the cosmic background as it radiates. It will be a black dwarf. A cold, dark, dead sphere of crystallized carbon and oxygen, supported by electron degeneracy pressure, invisible against the blackness of space. No black dwarfs exist yet. The universe is only 13.8 billion years old. The time required for even the oldest white dwarfs to cool completely is estimated at quadrillions of years or longer, perhaps 10 to the 15th years or more. The universe has not existed for even a tiny fraction of this time. Every white dwarf that has ever formed is still glowing, still radiating, still cooling. The oldest and coldest ones have surface temperatures of a few thousand degrees and glow dimly in the red and infrared, but they are still warm, they still shine. The era of black dwarfs lies inconceivably far in the future. When that era eventually arrives, the universe will be a very different place. The stars will have burned out long ago. Star formation will have ceased as the raw material, the hydrogen gas that fuels new stars, was used up or expelled from galaxies. The galaxies themselves will have dissolved, their stars scattered into intergalactic space by gravitational perturbations over trillions of years. The cosmic background radiation will have cooled to nearly absolute zero, stretched to incredibly long wavelengths by the expansion of space. The universe will be cold, dark, and nearly empty. And in that darkness, the black dwarfs will endure. They will be among the last coherent structures in the cosmos. Dense spheres of crystallized matter, held together by gravity, supported by the Pauli exclusion principle, carrying the frozen remains of stars that burned billions or trillions of years in the past. They will drift silently through the void, invisible, radiating nothing, absorbing nothing, existing as pure structure without energy, form without function. They will persist for timescales that make the current age of the universe seem like the blink of an eye. They will persist until the protons within them decay, if protons decay at all, which is predicted by some theories of particle physics, but has never been observed. Proton decay, if it occurs, would have a half-life estimated at somewhere around 10 to the 36th to 10 to the 41st years. Even at the shorter end of those estimates, that is a number so unimaginably large that the current age of the universe, 13.8 billion years, is essentially zero by comparison. If protons are truly stable, if they never decay, then the black dwarfs will last forever, eternal monuments in an eternal void. There is something extraordinary about this picture. The same quantum mechanical rule that determines the structure of atoms, the same principle that gives the periodic table its shape, the same law that makes chemistry possible and therefore makes you possible, is also the force that will hold up the last surviving structures in the universe long after everything else has faded away. The Pauli exclusion principle is there at the beginning of matter's story, shaping the atoms from which stars and planets and life are built. And it is there at the end, holding up the cold remnants of dead stars against the endless pull of gravity in a dark and empty cosmos. White dwarfs are quiet objects. They do not announce themselves with violent explosions or dramatic emissions. They do not dominate the night sky. Most are too faint to see without a telescope. They simply exist, small and dense and slowly cooling, scattered throughout the galaxy in enormous numbers. Most stars in the galaxy will share this fate. The Milky Way alone contains an estimated 10 billion white dwarfs already, with billions more to come, as every modest sun-like star eventually exhausts its fuel. They are everywhere, beneath notice, but everywhere. And every single one of them is a testament to the power of quantum mechanics. Every single one is a star-sized demonstration that the universe operates according to rules deeper than fire and gravity. Rules about the identity of particles. Rules about the filling of quantum states. Rules that say two electrons cannot be in the same state at the same time, and that this prohibition, this quiet quantum stubbornness, is powerful enough to hold up a star. Inside a white dwarf, matter has stopped behaving normally. The atoms are gone. The familiar phases of matter do not apply. The pressure has nothing to do with temperature. The star is supported by a law of quantum mechanics that most people have never heard of. And yet this strange, exotic, deeply quantum mechanical object is one of the most common things in the universe. It is the default fate of stars. It is the endpoint of the sun's life. It is the future tomb of the very star that makes your existence possible. 5 billion years from now, the sun will swell into a red giant, shed its outer layers into a glowing nebula, and leave behind a white dwarf roughly the size of Earth. That white dwarf will contain the carbon and oxygen forged in the sun's core during billions of years of nuclear burning. It will glow white hot at first, then cool over eons to yellow, to red, to infrared, and eventually to darkness. And through all of it, for quadrillions of years, it will be held up by the refusal of electrons to share their quantum states. By the Pauli exclusion principle, operating at scales too small to measure, holding together an object too large to comprehend, in a universe too vast and too old to imagine. That is what happens inside a white dwarf. Matter stops behaving normally, and what takes over is something deeper, something stranger, and something far more enduring than anything the ordinary world has to offer.